Right, so I'm going to go through this question from start to finish the way you might get in a test question. So let's suppose 1960, %30 teenagers over 17 had a car. So in the past, in the 1960s, 30% of teenagers over 17 had a car. This is what we would say is a fact, right? We just know this is true. A social scientist thinks that this has increased. So he thinks it's got more. He thinks, yeah, there are a lot more teenagers now that have a car. Whether it's their car or not, that doesn't matter, that they have the, the ability to borrow a car even, right? But they have a car. And he believes it's increased. But he'd like to be able to see whether or not he can actually prove that that's true. Because that's what a hypothesis does, its job is. To see if you can prove a particular statement is true. Now, I guess the best way to prove it, wouldn't it be to ask every single teenager in America over 17, do they have access to a car? Now, if you did that, you would, basically, that's called the census, you would know the answer. You know, it's 42%, there's your proof. But that's very impractical, so it's almost never done, right? So what do you do instead? Well, you conduct a little experiment, you do a poll or a survey, as it's very often called, and you go and ask some teenagers, and they're going to be your sample. So let's suppose in this story, a sample of 1,030 students were asked if they had a car. And the answer was I'm trying to make this reasonably. And the answer was that 340 of them said yes. So that's our sample data. It's typically going to consist of two numbers. The number of people who said yes to whatever the question is, in this case 340, and the total number in the sample, which in this case is 1030. And now we're going to set up a hypothesis test to see if there is evidence that more teenagers today have a car. And there should be an extra piece of information at the end of the sentence, or even up here. And it's phrased like this: with a significance level of, and then they'll write something like alpha equals 0.01. This is very important at the end. It's not really going to have any effect until we get right to the end and we make our conclusion, yes, there is enough evidence, or no, there's not. And what does this number represent? It's kind of interesting, because what it really is telling us that when you do anything in statistics, virtually anything in statistics, you're never 100% sure that it is correct. All you can do is put a limit on how few times you're going to be wrong. So when a significance level is this number, that's 1%. What that means is if I do 100 tests like this one in 100 of them is going to say, yeah, there's evidence that the thing that you want to be true is true, right? There's evidence for it, go for it. 1 in 100 times, you're going to get that conclusion, and it's going to be wrong. So you can imagine that anytime you see or hear anything that says, we've proved that such and such a thing is true statistically, well, you bear in mind that what they're really saying, although they don't say that, is that we've proved it with a particular significance level. The normal levels that you will see are a significance level of 0.1, 0.505, and a 0.01. This is sometimes called a 1%, a 5%, sorry, a 10%, a 5%, or a 1% significance level. And some people are very sneaky about that. They don't mention anything about the significance level. They just say, it's been statistically proved, and then they go and say something. Well, you know, if something was statistically proved at a significance level of 10%, isn't there a 1 in 10 chance that they told you a pack of lies? That whatever it is that's true is actually not true at all. But they say it in such a confident way. It's been statistically proved, as if we are saying it's guaranteed to be correct. So always have that little caveat. Whenever you hear anything that says something statistically significant, always have that, yeah, but tell me the alpha level. Now, if somebody says it was 10%, I'm going to say, 1 in 10 times whatever you just told me is wrong. Now, if it's the one we're using, 1%, that's a bit better. And you know, you can actually keep going. If you make alpha 0.00, I don't know if you can see that, let's move up, 0.001, you can actually get a significance level of 0.1%, which means that only 1 in 1,000 times will you be wrong. So significance level is very important at the end, and it also is important to give you some kind of idea of whether you should, you know, sell your house and buy those shares or whatever, based on the thing that they tell you. So let's begin with the hypothesis process now. The first one is that you have to prove that you can do a, let's call it HT, so I don't have to keep saying hypothesis test. And there are 3 things that need to be true. And the first one is that the sample has to be random and independent. Okay, in my story, it was a random sample of 1,030 students. Yep, there's no reason for me to assume that they're not independent. So I will say, yes, good to go. The second thing is that the sample is big enough. You know, there's a test involving something being bigger than 10 that you can use to do that. And it's NP bigger than 10, right? And then 1 minus P bigger than 10. And in this case, it's true. And then the last one is that the population is big enough. And you get that by saying that you can phrase it 2 ways. You can say the population is 10 times bigger than the sample, or that the sample is less than 10% of the population. So technically, in every hypothesis test, you should be doing this check. If it fails on any of those, then you really shouldn't be doing a hypothesis test at all. Next part is you set up the hypothesis test. Well, it has a very strange format. It looks like this. H naught, you're going to say P, the population proportion, right? It's of today is still the same as it was in the past. So P represents the percentage of people today, students, who have a car, right? It's still 30%. This means there's no change. And the null hypothesis is always going to be that. So if you do another story where in the past it was 20%, H naught will be P equals 20%, 0.20. Now in this case, the alternate is P, and we want to see that it is increased. So that would be the alternate, and that means essentially it has increased. So there's your H naught to HA. I think in the homework questions, don't they just give you choices and you pick one of them? So you put a little dot next to it, so you don't really write it down. On to 3 then. This is going to be a change. We're going to collect the information we need. And use the calculator to get the p-value. So this is a change. I showed you how to do it the last time on a different lesson, how to do this by hand, but I've found that the calculator can do a better job, at least to make your life easier. So what's the information you need in these stories? You need to know X, X1, and that is the number of yes, and I'm being very cryptic here, yeses in your sample. And you need to know N1, which is the number of people in your sample. And you need to know a thing called P naught. P naught, P naught is 30%. P naught is this guy. So whatever the number in the past was, make that P naught. So let's show you how you can get the calculator to get what's called the p-value. So should be looking at this guy over here. So it's a different emulator, but it's fine. So let's show you how you get the p-value. You hit the start button. No, you don't. You have to hit on in this machine. Then you hit the start button. And then you're going to move over to tests. And then there's a whole load of different name tests, but the one you want is called the one proportion z-test. So for a hypothesis test with one proportion, you use number 5, one proportion z-test. Now when I hit enter, it's going to ask me for P naught, which is 30%. It's going to ask me for X, I'm calling it X1, and in this story, this is going to be the 340 students in my sample who said, yep, I have a car, out of a total of 1,030 students. Now, along here, you have the choices. And the choices are, is your percentage not the same as the original? Is the sample percentage going to be less than the original? Or is it going to be more than the original? So when I go down here, if I wanted to do a test, HA not equal to that number, I would use that one. If I wanted to do P less than 0.3, I would do that one. But that's the one I wanted. It's P greater than 0.3, so I'll hit enter. Then I'll go down, oh, it's already on it, and hit calculate. And in the, oops, I didn't hit enter. I'm going to do that again. I thought I had. No, I hadn't. Oh, that's interesting. Right. I definitely hit enter this time to see how it's greater than. So hit the thing. And the guy we want here is this P on its own. Do you see this little guy here? And so the p-value, that's what that is equal to 0.018. Okay, let me pause for a second. Quite a lot to take in there. Is there anything you'd like me to go over while I'm doing this? There we go. Are we happy about, we've got our story, that it's right now it's broken into 3 pieces. Prove that you can actually do a hypothesis test, then setting it up, and then collecting the data so you can get the p-value. So far, so good?
Yeah.
Now, have you noticed that this does a lot of the work you had to do by hand? So I think the calculator is quite a good benefit. It will save you some time, and it also make calculations easy.
Or you can use the StatCrunch too.
You certainly like that thing. Yes, you can. You're right. How easy is it to use? I've never used it, so I can't talk about it.
Oh.
Easy, average, hard?
Oh, easy.
Easy. Oh, good.
Yeah.
So where are we off to next? Well, we're on to our final step, step 4, conclusion. We've checked I can do it. I've set up my hypothesis test. I found my p-value. Now I need a conclusion. The conclusion is going to be, yes, there is enough evidence to prove that students have more, have a car more today than they did in the 60s, right? Or there's not enough evidence to prove that. So here's your test. You just check, is the p-value less than your significance level alpha? In this case, the p-value was 0.018, and we had to check that it was less than 0.01. Is that true? Is 0.018 less than 0.01?
No.
No. So we haven't found evidence to prove that students today have a car more than they had in the past. So the sentence that you do when you get a no out of this is, the lawyer version of the sentence is, there is not enough evidence. To reject H0. So in English, we have not proved that teenagers today have a car at a greater rate than they used to have in the past. Now, that alpha came in right at the end. In fact, the alpha being that number was why we got no. Pretend for a minute that the alpha was 0.05. So imagine right at the beginning of that question, I made alpha a 5%, right? 0.05. In this case, won't the answer to is the thing right? Won't the answer be yes? This is less than that. And when that happens, you will write down there is enough evidence to reject H naught. But you finish with, and so HA is true. And in English you will say, we have proved statistically.
I'm confused, sir.
Right. Well, I'll finish this sentence and I'll come back to your confusion.
Okay.
So it proved that statistically that students today own a car more often. So I guess your confusion is, well, you tell me what you're confused about.
Based on the exercises that I've got on
Yes.
homework on chapter 8, if the significant or if the p-value is less than significance levels, for example, 0.05,
Yes.
it should be reject, and the conclusion is reject, and
All
yeah.
have they written it down this way?
Mm. Yeah, if that's the case, if it's greater.
Right. Alpha p-value less than alpha is the same thing as alpha bigger than p-value.
Mhm.
So it's the same thing. 5 is bigger than 3 is the same thing as saying 3 is less than 5.
Oh.
So I'm not sure what they're doing. I wish they hadn't. The usual test that you will see is that the p-value is less than alpha. That's the normal order that you check things. So you want a p-value to be less than alpha to be able to reject the null hypothesis and the alternate is true. That make sense?
Yes, sir.
Okay. So if they've phrased it some other way, I'm a bit annoyed at them, but we can't help that. And this is the way that it should be done. And what I was getting at in this question is something that you will also have to be skeptical about when people tell you they have proved something statistically. Do you know when I had the significance level of 1%, there wasn't enough evidence to prove that teenagers had more cars, right? But when I changed the significance level to 5%, it now says that there is enough evidence. Can you see what could happen here if you were an unscrupulous person? Wouldn't you first do the entire hypothesis test, wait until you knew what the p-value was, and then decide which alpha you were going to use so that you could get evidence to prove what you wanted to prove in the first place? You see how sneaky that can be?
Yeah.
And so that's why if you ever are in the nursing, or if you're in social science classes, or you're in something and that's what your major is, and they do studies and they tell you information about we've proved this or we've proved that, they've always done this statistically. It's always been, or it should always be at least, hypothesis testing. If you get into the kind of small print at the bottom, you'll then see the p-value and the significance level alpha, or at least at a bare minimum the p-value. And then you can have a look at that and you can see whether or not you should be as confident as they say they are that they've proved anything. And me personally, I don't like the significance level of 10%. Because if you think about it, I could be, if I do 10 surveys, I'm going to be wrong one of them. I don't think, if I was charging someone for a crime, do you want to be, if you were a lawyer or whatever a person, do you want to have it so that 10% of the people you send to jail were actually innocent? Yeah, we've got enough evidence to prove that person's guilty. Stick him in jail. I don't want to live in a society where alpha is 10%. Because there are too many people who are innocent get caught with that. I don't want to do a new drug where the alpha, the significance level was 10%. Because that means if you have 10 drugs out there, 1 in 10 doesn't work the way it's meant to. It's not actually a better drug. It's a worse drug, perhaps. So just be skeptical of it. Any other questions about that one? Okay, yes.
This is chapter 8.
This is 8.
So on the fourth one where you did the conclusion, you said
Yes.
that the p-value is not less than 0.01. Is 0.01 what we're always going to be compared to, or where did you get that number?
That 0.01 comes from the question. So right at the start of the question, they should have said significance level alpha equals 0.01. And in the question that I started with, that was in the storyline.
Okay.
So they have to tell you this. And what I'm saying is that you could go back and change that storyline and make that alpha a different number. And in that case, you may end up with a different conclusion because of that.
Okay.
Ready?
Yes.
Next fella. Now, some of you were here, but not that many. So this is a biggie. And this one's going to cause you hassle. So the last kind of hypothesis test that you need to do is a hypothesis test using 2 proportions. So I am going to hopefully zoom over and show you that. Oh, I was there already. No, I wasn't. Try it again. Let's look at this one more time. There we are. So you're looking at a screen now that has a calculator on it and some written stuff to the right. Is that what you're saying?
Yes.
Okay. So I've got here using hypothesis test, or a hypothesis using 2 proportions. So this is like the ultimate hypothesis test, and very often this is more likely to be the one that you'll end up doing if you ever have to conduct surveys or do any kind of analysis, any kind of experiment. So a survey was carried out to see if there's enough evidence to prove that Scottish people drink more whiskey than Americans. So what did they do? Well, they asked a random sample of 400 Scottish adults, did they drink whiskey regularly? And 250 said, yep. And then they asked another sample of 300 Americans, the same question, and 160 of them said they did. So is there enough evidence based on 2 different samples, right? Americans and Scottish, right? Is there enough evidence to prove statistically that Scottish people drink whiskey more often than Americans? And that's the place where the alpha will be given to you. Almost always is the last thing you see written down. So in this case, it's going to be a 0.05. So we're going to go through a little bit quicker because you can certainly read this on the video if you need. Is it a random sample? Is the sample random and is it independent? Yep, the storyline didn't make me think it wasn't. Are the samples big enough? If you do that NP thing to all of them, the answer is everybody's bigger than 10, so it's yes. And I'm sure there's enough people in America and in Scotland to conclude that the population is large enough. So we are good so far. So second part, set up your hypothesis test. Now here it's a little bit different. We're going to let P1 represent the true population of Scottish adults who drink whiskey, and P2 be the Americans who drink whiskey. And the null hypothesis is now going to be that P1 is the same thing as P2. So in this world, the assumption is that both countries are equal. They drink the same amount, of whiskey as each other. And in the second one, the Scottish guy, P1, is bigger than the American P2. So we want to see whether or not there's enough evidence to prove that Scottish people drink more whiskey than Americans, which was what was being asked here, right? So this blue bit is where I figured out that I wanted to do that. If they had said, prove to me that the first lot is less than the second lot, then I'd make that a less than symbol. And if they said, prove the first lot is different, I don't know how different, but it's different, it's not the same as the second lot, then you put a not equals to here. And then you come to step 3. Now, trust me, on a 2 sample proportion, this calculator is going to save you chunks of time. But we need to know some things. X1 is the number of Scottish whiskey drinkers, N1 is the sample. X2 is American whiskey drinkers, N2 is the sample. I need these 4 numbers. And we are going to find that p-value. You can see what it is right now, but let's show you where it comes from. So here goes. Hit start button again. Move over to tests. And you see number 6. We were using number 5 earlier today. Now we're going to do number 6. We are going to do a 2 proportion hypothesis test. I'm going to enter. And it's asking me for these numbers here. So how many Scotsmen drink whiskey? 250. How big was the sample? There were 400 of them. How many Americans drink whiskey? 160. What was the size? 300. And now we have the same choices. Is P1 not equal to P2? Is P1 less than P2? Is P1 greater than P2? And can you remember in our story we wanted P1 greater than P2? So when we go down there, we make sure that we choose that one, which I have. And when I hit enter, here is the p-value, 0.0074. That's where that came from. Kind of cool. All you need to do is tell me how many people in the sample, how big was the sample, how many in the second sample, how big was it, and the rest is done for you. We now have the p-value. Now, if you had to do that by hand, you'd have to calculate standard error, then you'd get z-scores, and then you'd have to use the normal CDF. So if you go through that process, that's doable, but much longer. So what's left? What's left is conclusion time. So we want to see, is there enough evidence to prove that our guy, the alternate, is true? Well, is the p-value less than alpha? That's our test. Our p-value is this guy, and he's less than that alpha, and the answer is yes. And 0.007 is less than 0.05. And because we said yes here, we can state that there's enough evidence to reject H naught, and so the alternate is true. And that means, in English, we can say quite confidently that this statistically significant proof that Scottish people drink more whiskey than American people. Right, there's a lot to take in there. Is there anything you'd like me to maybe explain in a little bit more detail? Are we good with this process of how do you compare 2 different samples to see whether one sample is bigger than the other or less?
Yeah.
Okay. Right, I'm going to have to do a very quick one because of our time. There is a kind of slower version of this online, but this is so big that I don't want you to miss it, and I know a lot of you didn't turn up for the last one, and I'd hate for you not to miss out on this because you skipped by that lesson, didn't even realise I was doing it. Okay, so in this one, this is very common in the medical field. And basically the problem is, how do you check that a new treatment, a new pill, a new procedure, whatever it is better than the old one? Because if it is, what you can then do is publish in a medical paper like The Lancet. Hey guys, this new procedure is much safer on patients. So this is a better way to do a hip replacement. Or this pill is much better at reducing heart rate palpitations or reducing blood pressure, whatever it is. We have to do what is called a clinical trial in these circumstances. So in this story, a clinical trial was conducted to see if a new medication was more effective at reducing the death rate than a generic drug. In lots of very serious illnesses, no matter what you do, people are going to die. And so what you want is a drug that stops them from dying, right, basically. And sometimes you find that when they record the p-value, the percentage, it's actually quite a negative kind of thing. The percentage here is people who die. You would think that would be people who live, but they don't always do it that way. So in this clinical trial, which was a double-blind trial, the new drug had a fatality rate of 6% and was tested on 200 patients, and the old drug had a fatality rate of 8%. If you want to be an optimist, if you took the new drug, 94% of you lived, and I'm assuming got better. And if you took the old drug, only 92% of them got better. Now, the new drug's better than the old, agreed at 6%, but is that evidence? Because it could have just happened by coincidence, right? If you just do two groups and split them up and do stuff, there's a bit of variation going to happen, and sometimes this might be the variation. They use a term here called double-blind. Has anyone heard that? A double-blind experiment, or a double-blind trial.
Yeah, where everything is random. The doctors don't know and the patients don't know either.
That's the one. Who uses that? It's almost exclusively done, although it can be done in other people. It's almost exclusively done in the medical field. And the reason they're doing it is because of a thing called the placebo effect. So you can read up on this, it's quite fascinating. If someone knows they're getting a drug and they believe that that drug's going to be of some benefit to them, even if that drug has got nothing in it that's pharmaceutical, right? It's just a sugar pill, they will get better to some degree. And some people get better a little bit more, and some it doesn't affect them. But there is a statistical change in the data. So I'll give you an example. If you've got a headache and a doctor gives you a pill and says, this will help you with your headache, if you really truly believe that that doctor's telling you the truth and you have that mindset, do you know taking that pill will reduce your headache? It might even make it go away. Strange, but it's true. So you don't tell anybody anything in a double blind. The doctors don't know who's getting the good pill or the bad pill. The patient doesn't know either. And we're going to do a test at a significance level of 0.1. So we do the first one, yes, yes, yes. Set up the hypothesis test. First, are they both the same? No difference in the two drugs? Or is the first drug, the new drug, doing a better job? It's smaller death rate than the other one. So we're looking for a lesser. Now here's where the change is a little bit different. We need to know X1, the number of deaths using the new drug. They didn't tell me that. What they told us is it was a 6% out of 200. But if you do a quick calculation, you see that's 12 people. And that's the number that you put in the calculator. You don't put 6% in, you don't put 0.06 in. You put the physical number of people that 6% of 200 in this case is. And then the same one with the other one is 32. And I'll go and we'll check this one out. I'll go over to tests. I'll do enter. Let's try that again. Too good, too quick for one good. So X1 was 12. Sample size 200. The old drug, it was 32 people. And that was 400. Only this time we're going to check is P1 less than P2. So the one I'm going to highlight is that middle one. Now when I do calculate, I get a p-value of 0.187, rounds off to 188. So I'll now do a test. Is the p-value 0.188 less than the significance level alpha, which was 0.01? The answer is no, and when it's no, you write down that sentence. So we can state there is not enough evidence to reject H0. So in English, it says there isn't any statistical evidence to show that this new drug has a lower fatality rate than the generic drug. And typically, if that happened, the pharmaceutical company that was doing that new drug would basically just say, well, that one didn't work. Let's just go back to the drawing board and do a new drug, or maybe adjust the one that we've got, see if we can make it better. And in the FDA, they will not approve a new drug for anything if you can't show that the new drug does a better job than the drugs that are already out there that do it. So there's not going to be a new blood pressure reduction medication until they can show that it does a better job at reducing your blood pressure than the ones that are there. So that's the gamble that pharmaceutical companies make. That I'll make up a number because I don't know the details. Can you imagine a pharmaceutical company every year generating 10 new drugs? Right? Their guys go in and they come up with 10 new drugs. Each one of those 10 drugs then goes into a trial where they do something like this to it. It could be as high as 7 out of that 10 don't make it. Right? They just aren't beneficial enough to go on the market. But you spent an awful lot of money and time on those 7. So the 3 that do go to market, do you know what they tend to be? And I've suffered this and I complain vehemently, but again, I sort of understand. When a new drug comes online, doesn't it cost an absolute fortune because it's non-generic?
Yeah.
Yeah. So you're thinking, why on earth are they charging $20, a pill? And when I was using the old generic thing, it's like, it's $1 a pill, right? Well, that $20 is to pay for the 7 failures as well. And of course, they got to make a profit or else the company will go bust, right? And so there's a lot of people out here right now looking for cures for the COVID-19. And what the government did, which is kind of interesting, and probably, in my opinion, I think the first time they've ever done this, so it's really quite innovative. They've said to the pharmaceutical companies, essentially, we'll pay for your failures. Because a lot of them wouldn't take on the risk. Because you could spend absolutely millions and millions looking for the cure and not get it. And that's you out of pocket. So what the government's saying, go for it. We'll foot the bill if you don't make it. And what that has done is it's made the likelihood that we're going to get something happen really quickly. Now, there's no guarantees, but at least it's going to make it likely. If you hadn't done that, a lot of companies might have thought, oh no, that's too expensive and we might not win, right? Some other company might get there first. We can't afford it. So that is us for today. Is there any questions?
I have a question, but it doesn't have to do with that.
Is there something you want to talk to me at the end about, or is it okay to share? It's up to you.
Either or. I did the homework 7.5, and I'm actually reviewing it on my laptop right now.
Yep.
On question 5, I could get everything, and I do not know how to calculate the intervals. It says the 95% confidence interval for the difference.
Gotcha. Right. So if you want to, Anybody who's interested in seeing that answer, hang around. If you're ready to get on with your homework in life, then you can go away. I'm going to show on the calculator how you can get a 95% confidence interval, right? Okay. So anybody who wants to see how to do that, please
Yes,
hang
sir.
around.
Mhm.
Okay, bye-bye to those who are gone. Usual, shoot me an email, whatever, if you've got some problems. So I need some numbers here to go with this thing. So can you tell me what the storyline was? There'll be a sample size. How big was the sample size? Do you know?
It says in a study, 106 children of a certain race in a certain city were randomly assigned to one of two groups. One
Okay.
group enrolled in preschool and the other did not.
Okay, so we've got a group called 1, a group called 2, and one is preschool, and the other is not. It was a little table, if I can remember.
Yes, and then
Right.
it's the
And then
ones
it was
that-
passing high school and not, right? So there was some who graduated and some who did not, right?
yes.
Right. So there's going to be a box with 4 numbers in it. Could you tell me what those numbers are?
Yeah, for the preschool, the graduated high school is 39, the did not is 12. And then
Okay.
for the no preschool, the graduated high school is 32 and the no grad high school is 23.
Okay, now I'm going to zip over to the screen where everybody can see that, because there's a lot of things happening here that you probably need to see. Okay, so in our story, we're going to find a confidence interval. What size did they want? A 90%, a 95, a 99? What did they ask for?
It says calculate intervals the 95% confidence interval for the difference between P1 minus P2.
Okay, so that's what we're going to get. So let's get some labels going here.
Sorry, sir, I have a question. So is this, you said, Candice, is this section 7.5, chapter
Yes.
7?
Yes,
Yes, I believe
okay.
she said 7.5.
Okay.
It's question 5.
Okay.
If you go to your grade book, you can actually
Yeah.
click on it and it'll let you review it without changing it.
Yeah. Yeah.
Okay, so we're looking at this guy now? Right,
Yes.
so we're going to have P1 being the proportion of people who graduate high school who did preschool. God, that's a long title. And P2 is going to be the proportion who graduated high school who did not attend preschool, right? So that's how I'm going to do the split. Hopefully that's the way they phrased it. So what do I need? Well, essentially I've got everything that I need here. And we can get the calculator to do that, but what the formula looks like is P1 hat, take away P2 hat, plus or minus a magic Z score, and based on a 95 confidence interval times the standard error. So if you were doing everything by hand, this calculation down here would be the job. Now, in this case here,
Can you take that paper and scoot it up a little more?
there we go. Is that enough?
Thank you.
Right.
Yes.
So P1 hat, preschool, 39 graduated out of a total of what, 51? And P2 hat, 32 graduated out of a total of, I think it's 55.
Yes.
So can you imagine, I'm not doing this, I'm actually going to show you the calculator way of doing it, which is much quicker. I'd find that guy, and they two would be subtracted. And then, do you know that there's a special number for the Z score for the 95%?
Yes,
know
I
what
have
that
that
number-
written down. The 95 is 1.96.
Correct. So some stuff there. And then there's a formula that you go and look up for the standard error. It's a big ugly formula and you could type it in. Well, let's show you how nice the calculator is. What it allows us to do is to find the whole thing, right? So we're going to find a 95% confidence interval, and we're going to do it by using the calculator. So I'm going to drop out of this one and drop back into the screen with the calculator on it. So here goes. And try to remember where the damn thing is. It's only two places. Okay, where the heck are you hiding?
It's on the test, sir. Same thing on the test at number 11, I think, or A1.
Oh, that's it.
Yeah.
So it was in the damn place. I just didn't look far enough.
Yeah, there you go. The test.
Yeah.
And
Yeah.
then
Right, so we're going to go down to it's A or B if I can
A.
recollect.
There you go, A1.
Right, so in this case, A1 is for a 1 proportion interval, but B is for a 2 proportion.
2 proportion.
And this is a 2 proportion story, so it will be B. So I'll hit that. And it says X1. X1 is 39 people out of a total of 51. So 38, did I hit 9 there? 39 people out of a total of 51. So these are the preschool people, right? 39 graduated out of a total of 51. Now X2 and N2 is going to be the second column, the people who did not do preschool. In this case, it's 32 divided by 23. So you put in X1 and N1 of the number of people in sample 1 divided by the total number in the sample. X2 is the same for sample 2. And then we got this fella. We want 95%, so 0.95 is fine. But if I wanted a 99, I'd do 0.99 and so on.
Is it,
So,
sorry, sir, is it 23 or 55? I think N2 is 55.
oh, well caught. Where did that 23 come from? No idea. Okay. That's what I get for being too quick. Well caught. That one's right, that one's right, that one's right. This one was 55. Now we're good. And ready to calculate. Now when I hit calculate, it is going to give me that weird interval that you were hoping to find. And here it is. The difference between these two is 0.00811 to 0.35766. It even tells you other things that you might or might not want to know. 76% in the first group, 58% in the other group, right? Now this is the confidence interval as a decimal. If you multiply it by 100, you get that answer. It's a huge interval. I mean, if I'm really rounding it off a lot, then the difference between these two groups is either 1% or it's 36%, and anything else in between. So it does mean, doesn't it, that the first one is bigger than the second, right? Because if it's a positive difference, the first number, right, the preschool percentage, has to be more than the second number, the not preschool percentage. So I can look at that and I can say, you know, there's some evidence that preschool does help you graduate. It could be as little as 1% more will graduate because they went to preschool. Or it could be as high as 36%.
Okay.
What reason do you think is causing this interval to be so huge?
I feel like because there's a lot of other factors besides just preschool and no preschool.
Well, that is true. That could, in itself, that will cause that same issue. But statistically, the main reason is that aren't these samples tiny?
Oh, yeah, yeah.
And tiny samples just make your all intervals big. In reality, if there's a lot of different factors between, you know, what makes you graduate from high school and what doesn't, that also will affect this. But what it might do is it might not affect the size. What it might do instead is it might make your answer something like this, where the range is between -4% and 5%, in which case going to preschool didn't necessarily help you graduate from high school. In fact, in this age, this range, 5% better, but over here, 4% worse.
We're still seeing the calculator.
You are? Okay, let me kick back in and see if I can make the calculator appear. No, that's not the one. Where are we? Oh, I know where it's hidden. I have so many different buttons to press to get anywhere. Here we are.
Okay.
Right.
Thank you.
There. So, yeah, that is, you know, that has problems, because if you ever get a confidence interval that has negative and positive numbers in it, then you can't really tell for sure if one of them is bigger or better than the other. Could be -4, right? Could be +5. But certainly doing tiny sample sizes is not a good idea if you want your interval.
And when you put it in the calculator, I think I found out where I was going wrong is because for the oh man, I just had it too. For the I kept putting 106 for all of them. So you're gonna do just the sample size, like we're doing just the ones that went to preschool.
Yes, yes. So it's 39 out of 51, and it was 32 out of 55. The 106 is a kind of red herring. It's basically everybody, but the 106 we do not need, because we're using the calculator to get the interval. That 106 appears in the hand calculation formula. So if you go and look at the hand calculation formula, you might find there's a big N in there, and that's maybe why they told you. But it's kind of relevant to getting a confidence interval by using the calculator. In fact, it's a lot easier, I think, this way. And Jamie will say it's easier in StatCrunch, right?
Yeah, I found it in the Star Scratch. I watched the video that you sent.
Yeah,
So
and
there's
they are good.
Yeah.
Keep doing it. No biggie there. We only have until Sunday midnight. My guesstimate, my gut feeling is that this is going to be your hardest test. Well, maybe the final will be, but this definitely will be the hardest. And so you need to get up and running so that you get a good grade for it. At least I've given you the advantage of showing you how to cut down on a lot of the places where you may have got, you know, caught up in the weeds by letting the calculator do some of the heavy lifting for you. Okay.
Do we only have 2 tests left? This chapter, this
we have,
one and then...
what we have left is this test coming, and that's the last test, and then after that it's a final. So week 9 will only have a topic that involves homework. It won't have any test associated with it. And then the final is a cumulative final, so you'll get questions from all your sections.
Is it on the 18th?
Couldn't tell you off the top of my head. Do you know what time this class was originally scheduled to be if it had been on the ground? Because that's going to be how I know when the test is due.
June 19th. June 19th is the spring quarter ends.
Yeah, but that's not necessarily the day the test is. It just means the test has to be done by Friday. But it could be done Tuesday, Wednesday, or Thursday.
Right. This class was scheduled, I want to say, Monday, Wednesday, and Friday from 1 to 3.
Okay, so what I can do is I can go, there's a schedule I've got that says if a class was Monday, Wednesday, Friday, 1 to 3, this is when you do the final. And by doing that, I'll be able to give you a time that won't clash with any of your other finals that you might be getting online from other classes.
So you mean the final is open for that week, for Monday, Wednesday, Friday?
No.
So it's up to us when.
No. What I mean is that I'm going to go and look up and I'm going to find out, I'll pretend, don't quote me because this isn't the answer. I'm going to find out that your exam is on Wednesday from 12 to 2, just for example, right?
Mm.
So your exam will be 12 to 2. Now what's going to happen there is that it will open at 12 and it will close at 2. It will be a very small window.
Are we gonna know ahead of time? Because I don't
Yes.
worry about my.
As soon as you leave, I'm going to go and check that thing. I have to go and hunt for it. And as soon as I've found it, I will shoot you out an email telling you when.
Okay.
So
Okay,
you'll
yeah.
probably get it within the next 15 minutes if it takes me 5 minutes to find it.
Okay. Okay. Awesome. Because I worry about work. I would like to ask for that maybe time off.
Okay, gotcha. That makes sense.
Yeah.
So,
Sir,
yes.
one more. So can we know now what are the chapters included on finals?
Everything.
Everything from 1 till 9.
Okay.
So ours has been kind of weird and lucky that week 1 was chapter 1 and week 9 is chapter 9. So you can even tell which week we must have done something by its number.
Okay.
So yeah, cumulative. Although you will find that some chapters don't have as much in them, and so you might not get as you won't get as much asked because things get used a lot. You know, like calculating probabilities and things. You use that in so many different sections that there's no, you know, whatever. Not every chapter is equal as far as questions go in the final. The stuff we're doing right now, for instance, is much more important than some of the earlier stuff where they say, you know, find the mean and standard deviation of some data.
Would you happen to know how many questions, or you haven't done the final yet?
I haven't done the final yet, so don't know. That's a short
Okay,
answer.
and I went back to review because I was working yesterday, so I missed your Zoom yesterday.
Yeah.
But there's no video for yesterday's Zoom for me to review.
Oh, and let me take a note of that as well.
'Cause I
Now,
wanted to,
the video will be put in the Zoom page.
okay.
So go look in there and look at the slot, and I'll go and double check. I
Okay.
thought I'd put it in, but evidently I haven't.
Okay. Yeah, I was looking under the modules for chapter 8, and I didn't.
Right, so if you go into the Zoom, I don't know what the file title is. It says something like Zoom meetings and times. That one there.
Okay.
When you go in there, the top tells you when Zoom meetings are, but there are little tabs for every week, and if you go looking in there, you'll find Zoom meetings. But I'll do a double check to make sure that it definitely is.
It's in there, sir.
Okay, it's in there.
Okay.
It says
Yeah.
me one last check.
There's 2 video on week 8.
Okay, I was just under the wrong thing. Okay.
Yeah, that's all. Easy done. And I'll this one that we've got. It takes a long time to do these because they have to get processed before I can even put them on YouTube, and then I have to copy them over. So don't expect to see this video anytime in the next 4 hours because
No,
I have classes that I'll be teaching as well.
no
But
problem.
you will get this video on sometime by tonight.
Okay. All right. No, I just wanted to make sure that I had a chance to review yesterday's Zoom since I was at work and I missed it. And
Right, we're good to go then. I'm assuming that is it, everyone.
Yes,
Yeah.
sir. Thank you.
You are welcome. Bye-bye. Bye-bye, Sarah, Chelsea, Candice, Jamie, Shanette. I think I got all of you. No, Matthew. Thank you, Matthew. Got you all now.
Thank you.